So we have this galvanometer of full-scale deflection. A question says the WAEC of 2024, galvanometer of full-scale deflection, 10 milliamperes has a resistance of 5 ohms. Calculate the shunt needed to convert it to measure a current of 2 amperes. So this is what the setup looks like. Full-scale deflection, that means the maximum current that it can take is 10 milliamperes, and 10 milliamperes is 0.01 amperes. It has an internal resistance of 5 ohms. So this is our galvanometer. I want to adapt it so that it can convert it to a current, so that it can take a current of 2 amperes. So we need a shunt, a resistor in parallel to this. Okay, that will take much of the current. Remember, a shunt is a resistor in parallel with the galvanometer. So this is our galvanometer, and this is our shunt, our resistor in parallel. So it's called a shunt. So it's taking much of the remainder current. So if 0.01 ampere passes out of this 2 amperes, take 0.01 ampere out of 2 amperes, we're left with 1.99 amperes. So remember, they are the same potential difference. So the potential difference between their ends, see, they're in parallel. So since PD across shunt equals PD across galvanometer, across the galvanometer we have a total current of this, a total voltage of this, current times internal resistance. So make our resolve the formula, we get this value. Look at this question from WAEC 2022. Says 3 cells, each of EMF 1.1 volts and internal resistance 2 ohms, are connected in parallel across a 3 ohm resistor. Determine the current in the resistor. Okay, so this is the diagram. You can look close in there. So it's 3 cells, symbol for cells, 3 cells in parallel. Of course, this is the connection, and they have each 1.1 volts and internal resistance of 2 ohms each. So that's what it looks like, all right? And they are connected in parallel to an external 3 ohm resistor. All right, so now let's to solve this question, we have to use the formula that connects. Remember the formula that connects internal resistance, small letter R, external resistance R, current, and EMF. So for cells in parallel like this, the effective EMF is the EMF of one of the cells. So we're going to use 1.1 volts effective EMF. And for cells in parallel, of course, do our total resistance parallel inverse. So you do that, use the LCM of 2, then you have 1 plus 1 plus 1, so you just add up 3 over 2. So you get 1 over R total is 3 over 2. So R total is the inverse of 3 over 2, which is 2 over 3, and that's 0.67 ohms. All right, so we've calculated the internal resistance, the total effective internal resistance for the 3 cells. Okay, so we'll now put that into this formula. This formula that connects, that helps us to determine the current in the resistor. All right, so this formula, making I the same with the formula, we can make I the same with the formula. So E will divide the sum of the external and internal resistance here. So I is like this. So putting your values 1.1 over, remember the external resistance is the resistance across this resistance here, 3 ohms. So that's a capital letter R. So put that into this expression, 3 plus 0.67, and you get 3 amperes. So let's talk about galvanometer conversions. There are ways we can convert galvanometer to, a galvanometer measures only small currents, but the galvanometer can be converted into an ammeter to measure larger currents. Galvanometer measures currents in milliamperes, while an ammeter measures currents in larger values like 1 ampere, 2 amperes, and the likes. So how do we do that? By placing a small resistance in parallel with the galvanometer. So this small resistance in parallel is called a shunt. So it looks something like this, in parallel with the galvanometer. So this shunt diverts the current in excess. So let's consider this example. We want, okay, like I said, that the galvanometer, this is our galvanometer. It can only measure, it has a full scale deflection of 50 milliamperes. Okay. And we want it to be able to measure current of 2 amperes. So what's going to happen is 50 milliamperes will pass through, and the larger current of the remaining currents, if you subtract 50 milliamperes from 2 amperes, you're left 1.95 amperes. Okay. And so the 1.95 amperes will be diverted through this smaller resistance. Okay, because the smaller the resistance, the more current can pass through. basically we're just taking advantage of our knowledge of resistors in parallel, all right, and the fact that the smaller the resistance, the more current it can allow through. So this galvanometer can only take a current of 50 milliamperes. This is about 0.05 amperes. Okay, and has this internal resistance. So the question is, let's calculate the value of the resistance, the value of the shunt, which will be able to make this 2 amperes possible through this setup. And so remember that they are at the same potential difference, between these wires. The potential difference between the ends of this our shunt, okay, this our attached resistance, is the same potential difference between the ends of this our galvanometer that we are trying to adapt. So this setup, they go together. So it's going to adapt this galvanometer to be able to pass this current. But of course, it's not going to pass all the current. Much of the current will be passed through this. So they go together. So the potential difference across the shunt is, across the galvanometer is the resistance times the current. Remember, V is equals to IR. So we just have this equation because they have the same potential difference. So for our galvanometer, we multiply this together. So for our shunt, current times resistance, we're looking for this particular, the value of the shunt. So R is our unknown. So divide both sides by 1.95 and you get that your answer is the value of the shunt that is needed to make this galvanometer, to adapt this galvanometer to this huge current is 0.128 ohms. Thus, a small resistance shunt of 0.128 ohms will convert a galvanometer into an ammeter reading up to 2 amperes. So to convert a galvanometer, conversion to a voltmeter, how can we convert a galvanometer to a voltmeter? So we use a high resistance multiplier. Okay, so the term is called a multiplier, high resistance wire, okay, in series with the galvanometer. Okay, should place in series with our galvanometer. So let's consider a galvanometer whose full scale deflection is 10 milliamperes. All right, and it has an entire resistance of 5 ohms. The potential difference across it, V1 is going to be calculated at 0.01 times 5. Remember, we're getting 0.01 from 10 milliamperes. Convert this to amperes, you get 0.01. So times this, so that's the voltage. So this is what it looks like. It looks something like this. So this is our galvanometer. It has an internal resistance of 5 ohms, and it can only pass, only a current at full scale deflection, can only pass 10 milliamperes. All right. So this is what it now. So you get a multiplier, you get a resistor, a huge, we get a resistor. So the resistor is going to pass. Remember, they are in series. So the current that is passing through this resistor is the same current that will pass through our galvanometer. So since the same current flows through both resistances in series, and you know that resistors in series splits the voltage in two. All right. Before we continue, I must say that what we're trying to do here, we're trying to adapt our galvanometer into a voltmeter. So we can adapt it. We want to adapt it to read voltages of up to 20 volts. That's why you have this 20 volts here. We want to be able to read voltages to up to 20 volts by using this setup. Okay, so 20 is 20 volt, and this is our multiplier. Okay, is in series. A high resistance in series with our galvanometer is called a multiplier. So it's going to split this 20 volts. So I know that our galvanometer can only take 0.05 volts. We just calculated it from here. That's current time. All right. So we've calculated. So this the galvanometer is going to take voltage of V1. So V1 is basically, remember from Ohm's law, V is equals to IR. That's current and resistance. So the current is taken is 0.1. So at full scale deflection, it can only take 10 milliamperes at full scale deflection. So 10 milliamperes is 0.01 amperes. So we calculated V1 as 0.05 volts there. So that means that our multiplier can take the remaining out of 20 volts. So subtract that, you get our multiplier can take 19.95 volts. Okay, so this V2 is 90. So divided by 0.01 amperes. All right, so our 0.01 amperes here, 0.01 amperes is current that usually it's this common current, okay? They're in series, so the same 0.01 amperes that flows through our galvanometer is what flows through our multiplier. Okay, that's our our resistor in series that helps us to adapt this galvanometer into a voltmeter that can read up to 20 volts. So divide your division. So voltage over current gives us the value of the multiplier resistance which we need, which is a huge value, 1995 ohms. So a multiplier of 1995 ohms is needed to convert the galvanometer into a voltmeter to read up to 20